Welcome back. We're in Projectiles unit, worksheet 3, number 5. An arrow fired 25 meters per second at an angle 60 degrees below the horizontal from the top of a 20-meter high battlement. How long it will be in the air, what's its range, and what will be its velocity when it strikes the ground. Great. Let's draw a picture. So I'm going to draw some little battlement there, the ground beneath that. That battlement is 20 meters high, so it's not too high. That's like a 6-story building. Somebody's up there with a bow and arrow. Here's my bow and an arrow. Give it some perspective there. Little feathers at the end there. His hands on that. Okay, yeah, that's good enough. Okay, so that's going, looks like he's got like a big bunny ear head on or something like that. Anyways, he's firing that arrow about that direction there. That's his original velocity. I'm going to put in the component vectors. I jumped around there. My horizontal velocity, my vertical velocity there. And so I know that this is going to be, well, I do know V naught, don't I? 25 meters per second. So if this is the angle right there, I should do that in a different color. If that's the angle right there, that's 60 degrees. So I guess I should have drawn it at a steeper angle there, but it's all right, I've already labeled it. And this one is 25 sine of 60 degrees, and this one is 25 cosine of 60 degrees. And I can label the green one there as what the green is, and that's 25 meters per second. Notice I don't label the 25 meters per second positive nor negative, as it's going in two directions there, and that's why we do the component vectors in blue there anyways. So I go and I label the path that it takes there, and it's going to take some sort of parabola. It'll be a pretty steep parabola there since he's firing it downwards already. I recognize a bunch of different things. I recognize, hey, if I looked at this arrow as it flies, anywhere along its path there, you know that gravity is going to be pulling this thing downwards, and that's going to cause it to accelerate downwards. Great. We know that acceleration is negative 9.8 meters per second squared. And what else do we know? We know how high that battlement is. Let's go label that. So this height, and technically, we should have said that the arrow starts 20 meters high. You'd say, well, because he's like holding it above the battlement there. Yes, you're correct. Didn't give us that information, so we'll assume that the arrow itself is 20 meters high. Let's see. I got all the information there. Got all the information down there. Great. So how long will the arrow be in the air? What's its range? And what's its horizontal velocity? So we can go label some of these unknowns. We don't know that range there. Chunk, chunk. How long will it be in the air? We don't know that. That's a big question mark. And what's its velocity when it strikes the ground there? So this velocity, we know it's going to be going something like that right there. And so then that will be some unknown velocity. Now, immediately, though, I'm also thinking, hey, that velocity, I could express that in the horizontal and vertical components. And furthermore, I'd probably need to, it'd probably be helpful to express it like that. Yeah, it probably will be. And there'll be some angle, theta, there. What is that angle? That's a good question. So we'll be answering all of that. I'm going to split this up into the x dimension here and the y dimension calculations. Give myself a nice little column here between the two, column break in between the two. A little bit less space for the delta x, as they usually don't have as many calculations going on there. Start with an equation that may be useful, and this is probably a pretty good one, as we're usually asking, or we're given, something about the horizontal range or displacement there. In this case, I don't know that, but I do know that the acceleration in the x dimension is 0, which gives rise to 0 times anything else is 0, so that whole first term goes away. V naught, again, that's V naught specifically in the x dimension, as we're only doing things in the x dimension under this column right here, multiplied by however long it's in the air. Now, we don't know how long it's in the air, but we do know how fast it was going in the x dimension. We said that that was 25 cosine of 60 degrees, so I can go ahead and fill it in. It's 25 cosine of 60 degrees right there, multiplied by whatever time that is, it'll give me my displacement. So I do need to figure out two of those variables. I can't do that right away, but that's all right. We'll go into the y dimension, see what's going on over there. Here, delta y is 1/2 at squared plus v naught t, and I ask myself, hey, do I know any of these things? Well, kind of. Delta y, well, I know that the height starts at 20 meters and it ends at 0, and 0 minus 20 gives me negative 20. Okay, cool. So that is negative 20 is my delta y, so I know that one. That's nice. My acceleration is negative 9.8. I don't know the time there, dang. But I do know the velocity there. The velocity is 25 sine of 60 degrees, and specifically it's negative 25 sine of 60 degrees. Okay, I put that negative out in front because I already recognize that that's going down, and I also remember from math that sine 60 degrees is going to be a positive value. So I assign the direction here. Now I look at this and I go, wait, I know everything except the time there, so I can figure out the time it takes to get down to the ground. Great, let's go do it. So let me rewrite all that. I don't know that you need me to. I take that negative 20 that's on the left side and I move that over to the right hand side, and I'll just put it down right now, plus 20 over there. I do the 1/2 negative 9.8 t squared plus my negative 25 sine of 60 degrees, and then I'm multiplying that by some time value. Okay, now I grab my calculator and I go to town solving that. I'm going to elect to use the equation solver there. So I just put it in as that, and put in negative 4.9 because it's 1/2 times negative 9.8. Put in x squared plus negative 25 sine of 60 degrees. Now the negative is easy to skip by accident, so don't skip that. I put in some guess that's very large and positive because I only care about the positive values. In this case, any of the others are erroneous. And I get 0.78 seconds. I store that in my calculator. In my calculator, it's already stored as the x variable there, since that's the variable I used. Now, if I went up and I changed this formula, instead of using x, and I actually used t squared and 25 cosine, or 25 sine 60 times t, when I go down to the guess, again, it gives me I guess something for t, something large and positive, and then it'll give me the exact same value, but it'll give me in terms of t, and then it'll be stored as t. So if you wanted to do that, you could always do that too. Anyways, doesn't matter. As long as you're operating your calculator correctly, that's fine. So now I go and, hey, that's the time to get down to 20 meters below where I shot it, and that's right down to the end there. So now if I go and take that time and I plug it into there, I'll figure out my delta x. So now my delta x is just that time. I stored it as t right now because I did go back and change it, times the cosine of 60. Notice I'm not using that rounded time, I'm using the full string, and I only round at the very final answer. So I get 9.81 meters. And so that is, both of these were actually some answers that they were asking there. So that's the horizontal range as well as the time that it'll be in the air. What's its velocity when it strikes the ground? Well, great. Well, what's the velocity in the x direction? Well, we know that in the x direction, the acceleration is 0, which means that the original velocity in the x direction is just equal to the velocity in the x direction. It doesn't change. It's never changing. And we know what that is. That is, as we just put up above this in black, 25 cosine of 60 degrees, and it stays exactly that the whole time. Okay, and that's pointed to the right, as we have in our diagram up there. What's happening in the vertical dimension here? I'm going to put a little colorful break there. I'm still in the y dimension on the right side here, but I'm separating one calculation from another so I don't get confused, and nor does my reader. So I look at that and I go, hey, what is the velocity at the end there? Well, I know the acceleration. And I know the time because the time is just that value right there. So I'm going to go ahead and put that in. I'll write that in as the approximate 0.78, but I'm going to use the whole string of numbers when I put it in my calculator. And then the original velocity was just my 25 sine of 60 degrees. Now careful, because that's a negative 25 sine of 60 degrees. Remember that velocity at the beginning there was pointing straight downwards. So I label that with the direction that it actually is. That'll make a huge difference. Now I go and grab my calculator and do all of that. Negative 9.8 times that t-value plus my negative 25 sine of 60 degrees. Make sure that you're in the degree mode for your calculator, since we're using 60 degrees. And you get the velocity in the y direction as negative 29.34 meters per second. And the negative shouldn't throw you off because you know that it's going to be going down at a faster rate than it was before. And if you're not sure if that's at a faster rate than it was before, you just go ahead and do this, just that calculation off to the side. Negative 25 sine of 60 degrees is negative 21.65 meters per second. So it clearly has sped up. And it's sped up by, notice it hasn't sped up by a factor of 9.8. Instead, about 3/4 of that it's sped up by, since the whole time it's about 3/4 of that. Okay, great. So now I have, let me redraw this actually. I'm going to draw the blue velocity vector to the right there. And we already know that that's 25 cosine of 60 degrees, so that hasn't changed. And then the purple one, though, the purple one is going down, and now that has changed, that vertical velocity has changed. It's 29.34 meters per second, and you know that it's pointing downwards. My total answer, though, is the vector sum, the summation of both of those things, but they're vectors here, so I can't just straight add them together. And furthermore, I got to figure out what angle that thing's at, and I'll label that as theta. So use my vector addition here, which using Pythagorean theorem, since we have a right triangle in here. And so I know now, maybe I should separate this, because now I'm not working in the vertical nor the horizontal dimension. I'm working in both actually. I'm going to put VT for V total. I've seen many people do that before. That's the square root of the sum of the squares. So 25 cosine of 60 degrees, and I square that, plus my 29.34, and the whole string of numbers. I'm not using that rounded value there. So I actually went and stored that velocity in the vertical direction as some letter. I just chose a random letter A squared. So I take the square root of first. Don't forget parentheses when you're doing the 25 cosine of 60, square that plus that velocity squared. Now don't worry about that the velocity is negative, because you're squaring it, so that won't matter anyways. So I get the total velocity, and I'll label that over here on my diagram. VT is 31.89 meters per second. You can't say it's positive or negative because it's going both to the right, positive, and down, which is negative, so it's both. Instead, we got to put some angle. And that's going to be at, we got to figure out that angle. So let's go ahead and let's do the tangent, since I have both of these values right there. The tangent of theta is equal to my opposite side, which is the 29.34, over the 25 cosine of 60 degrees. That 29.34 is negative as well. But I'm going to go ahead and I'm going to do it as positive, because I already know what the answer should be. The answer should be between 0 and 90 degrees, but negative. And we know that sine, cosine, and tangent don't always give you the positive and negatives correctly, because sometimes there's multiple answers to that, as you remember from the unit circle. So I get the tangent over on the other side by doing the inverse tangent. I take the 29.34 divided by, don't forget parentheses for the 25 cosine of 60, and I get, what actually gives me negative 66.92 if you put it in as these positive values. And I expect it to be negative as we're measuring clockwise down from the positive x-axis there, and that is the negative direction. So at 66, at negative 66.92, and everybody who reads that in the world will assume that you are measuring that from the positive x-axis and going the opposite direction as you normally do under conventions that we've already established, which is clockwise in this case. Cool. That's it. Have a nice day. See ya. Bye.